Hi guys, so today we are going to see how we can build Google search type functionality for our own AI apps. So what that means is like, say for example, right now I'm showing it from the Cloudy AI. So if we, for example, if we ask some search, say find customer named John Smith. I'm making the spelling mistake here on purpose. So this is can be done if it is a fuzzy search is working fine, right? So we have to build like Elasticsearch for this one. So that's what we are going to see in this video. So overall, there are like three sections in this video. One is the introduction to Elasticsearch and how it works for RAG and AI applications. Second is I will show you, give the demo how we can build this, and the third is we will do the in-depth architectural review and interview practice so that we can target this kind of jobs. Okay, so here, even though we say John Smith, it found John Smith and other similar terms. So this is what we wanted. So how we can build this, we'll see it. Okay, so let's start our video.
Hey everyone, and welcome. So, if you're a recent grad trying to land that first big AI engineering job, you already know the interview game has completely, and I mean completely, changed. Let's jump right in and crack the code on exactly what hiring managers are asking about right now so you can walk in there with confidence. It's a tough question, isn't it? But we have to face it. You've done the coursework, you've built some awesome projects, but then you get into the interview and it feels like the questions are coming from another galaxy. So, what is going on? And boom, here's your answer. The single biggest mistake people are making is studying for last year's interview. Right now, over 60% of the questions you're going to get are focused squarely on generative AI. That's not just a small change, that is a massive, massive shift. And this chart just lays it all out, plain and simple. You know, a couple of years back, if you knew your classic machine learning models, you were golden. Now, that's maybe a quarter of the conversation. The huge chunk, the part they're really going to dig into, is all about RAG. That's retrieval augmented generation, and AI agents. Your old study guide, it's just not going to cut it anymore. So, here's our game plan for today. We're going to break down this new interview landscape, we're going to totally demystify what RAG is, and then look at its absolute backbone, Elasticsearch. After that, we'll go beyond simple keywords with semantic search, and this is the best part, learn how to answer questions like a seasoned architect. Let's do this. All right, so first things first, what is this RAG system that everybody is so obsessed with? Well, at its core, it's the solution to a really, really big problem with large language models. Now, check out this comparison because it's key. A standalone LLM, you know, the kind you chat with online, it's basically making its best guess based on old training data. It has no idea what your company's private documents say or what happened in the news 5 minutes ago. So it often just makes stuff up. We call that hallucinating. But a RAG system, it fixes this. It adds a super important step. It looks up the facts in a knowledge base first, making sure its answers are actually grounded in reality. So the whole RAG pipeline really breaks down into two main phases. The first part is all the prep work. It happens offline. We call it indexing. This is where you take all your documents, chop them up into smaller, bite-sized chunks, and then you turn them into these numerical representations. We call those embeddings. Then you store them all ready to go. The second phase, querying, is what happens live. A user asks a question, and the system zips through storage, finds the most relevant chunks, and hands them to the LLM. It's like giving the model an open book test with all of the right notes. Okay, so let's talk about the engine that makes that whole retrieval part of RAG actually work. I'm talking fast, scalable, enterprise-level stuff. And that engine is Elasticsearch. It's way more than just a database. It's the high-performance heart of modern search. The real magic behind how Elasticsearch is so unbelievably fast is a data structure called the inverted index. So instead of reading through every single document to find a keyword, which would take forever, an inverted index is like the index at the back of a textbook. It maps every single word to a list of the documents that contain it. So searching for the word blue becomes an instant lookup, not a massive library-wide scan. It's absolutely fundamental to how search works. Now, in a real-world system, you'll almost always see these two working together. You've got a traditional database like Postgres acting as the source of truth. It's built for reliability, making sure no data ever gets lost. But for searching that data, it's kind of slow. So what do? You copy that data into Elasticsearch, which is built for one thing, speed. It's a super common pattern. Store it safely in one place, make it searchable in another. But modern RAG has to go way beyond just matching exact keywords. I mean, what if a user asks a question using totally different words that mean the same thing? That's where we get into something really cool called semantic search. And this table just breaks it down perfectly. So sparse retrieval, that's your classic keyword search. It's amazing for finding exact things like a specific error code or a product ID. Then you have dense retrieval. This is all about meaning and context. It's powered by those vector embeddings we talked about. But here's the secret. In the real world, you absolutely need both. That's why pretty much all production systems use a hybrid approach to get the pinpoint accuracy of keywords and the deep conceptual understanding of vectors. Now, listen up, because this is a point that will make you sound like a senior engineer, not a recent grad. It sounds totally backward, but just dumping more and more data into a vector database can actually make your search results worse. Think of it like a crowded room. The more people you pack in, the harder it is to find the person you're looking for. This proves that building a great RAG system is a real engineering challenge, not just a simple demo. Okay, so knowing all these concepts, that's one thing. But talking about them in a high-stakes interview, that's a whole other ballgame. Let's pivot now to how you can frame your answers to sound like a seasoned AI architect and not just someone who followed an online tutorial. Just look at the difference here. The student-level answer, "I'll fetch the top key results," isn't wrong, but it's basic. Now look at the architect-level answer. It talks about a pipeline that retrieves and validates internal knowledge and has security controls. See the difference? You're not just describing a single step, you're showing you understand the whole business problem, the need for validation, for security, for a real-world system. And this quote right here is why that matters so much. Companies aren't just looking for cool tech. They need AI that gives them context they can trust to make decisions with governance and safety built right in. So your job in the interview is to show you get that, and you do that by using the right language. Here they are. These are the keywords you need to start dropping into your answers. Don't just say you'll get documents, say you'll perform validated retrieval. Talk about using metadata-driven filtering to handle security, mention citations and confidence scoring to show how you build trust in the system, and for really important tasks, bring up a human-in-the-loop approval process. These are the terms that tell an interviewer you're ready for a real job. We have covered a ton of ground, from the deep-down tech of RAG and Elasticsearch all the way to how you talk about it like a pro. Just remember, the goal isn't just about giving a correct answer. It's about showing you can think like an architect, designing a secure, reliable solution that works in the real world. You now have the framework to do exactly that. Rajan, the stage is all yours. You may start the demo now.
Okay, now let us start the demo. So as we saw earlier, this is our cloudy desktop. From the AI, when we write this kind of queries, find customer name John Smith, it shows us John Smith and other related customers with similar names. So that means fuzzy search is working correctly. So this is what we are going to see how to build. Now the Google search is proprietary, so we cannot just take that Google search box and put it on our AI app. What we have to do is we have to build it ourselves. So we are going to be using the open source product Elasticsearch for that, and this is the code for that one. We'll see how to build it. So mainly I'm going to show you these three things. One is our server, SQL Server and CPPY. Then I have this readme file prepared and then we have this how to configure the cloudy desktop config file. So what we are doing here is we are going to be connecting with AdventureWorks, and then we are going to think of it like we are going to create a view, meaning we are going to take only certain part of the database for building our Elasticsearch. So only those, the customer data that we select, we will be creating Elasticsearch on that one. Elasticsearch, like basically to understand, uh, let me start with this. What's going to be our output we are expecting? So Elasticsearch is something like, think of it like last page of our books where we have that index where we can search by the term and it gives us the page number, this and this, so we can directly open that page and see what is about that search. So that makes it very quick. So that is what we are going to be building. So this is called inverted index. That's what the Elasticsearch will build for us. Okay, this is a traditional forward index. It's like the front page of the book where we have table of content, right? So that's it will be slow. We have to do like this kind of search. So what it will do basically is it's going to be creating from right now, because we are connecting with our adventure database. It's going to be creating this kind of file, a JSON file. And that is one thing. So JSON file plus that index. Okay, so these two things it will build. So we will be building it. And just to give you the structure wise where that files will be built, the files will be built inside the Docker container at these locations. Under share this, these things. So okay, and how do we set up the Elasticsearch? The command is this. This is the command to set up the Elasticsearch, and this will run Elasticsearch in the Docker container. Okay, so right now, for example, I have this Docker container and Elasticsearch is running, right? It's green and it is running. So now we saw the readme, what is going to be our output. Let us check this config file as well. So in the config file, we have mentioned this. This is our MCP servers. So right now we have these two MCP servers. One is PostgreSQL. We are connecting with PostgreSQL. Second is AdventureWorks. This is our focus right now. This is what we did earlier. AdventureWorks, we are going to be, we say that command and argument. Command is from this location. Cloud is going to run this Python, and this is our server. This is where it's going to be running this server. Okay, so these two things. And environment Elasticsearch, we are giving the port number and everything here. So this is where we can access it, and this is the search index, customer works customers. So this is the name we have given here. This much we have to configure here. Now in the SQL server, okay, now here what we have to configure in our server program. These are all the import statements. This is the server name. Cloudy will recognize our server by this name. Then Elasticsearch host and index. This is we are getting it from here, but it's the same name. Then we are creating a client here, client object here. Then so to see this one, it has basically the host name, authentication, and so this is how we are connecting it. Nothing special here. Then we have some helper functions here. This is just to make sure the data types are for our requirements null and all that. The important part here is when we talk about building that index, inverted index by Elasticsearch, this is the part that will do it. So in here, the important thing is this part, like select statement, right? We are selecting the data that we want in our JSON document and for the index. Okay, so we did the joins and everything here. Then we are doing the mapping here. We are specifying the data types, making sure all the data types and the sequencing is correct as per the select statement. Same way in this creating the document, we are saying that this is a string type and this is a date type. So all these format date and all these functions we defined earlier in the helper function. Basically it says how to format it. So this is where we are defining basically what we want in our Elasticsearch. So just to understand this thing, whatever we have defined here, this is what we can ask for the fuzzy search. Okay. The fields that are not selected here, those we cannot expect that it will use the fuzzy search. It might go with the SQL like statement. It can be very slow as well. So we have to be mindful when we are preparing this that we include whatever is needed here. Similarly, we have the list tools and call tools here. This is we have done before as well. So this is a listing of the tools. So when Cloudy connects and it says, okay, what tools can I access? It will list all the tools. So here, this is, we have a query tool, we have a table tool. So all these tools are listed here, search customers. So nothing new here. Listing of the tools here. Same with calling of the tools. So once the call is made, now this is how we will handle the calls, right? So search customer. Then what do we do? So this is the code for how do we handle that thing. Similarly, if the Cloudy says, okay, I want to sync the Elasticsearch, then it comes here and call this function here. We define it above, right? We just discussed. So it will create the sync, it will create the index. Similarly, the customer analytics. If some customer analytics like that kind of call is made, like aggregate the top 5 spenders, right? List top 5 spenders in Seattle, something like that, then we'll come here. Right. So if it is a table, right? So if it just says list the tables, so here what is different here is we are hard coding this SQL. The reason is we don't want the Cloudy to take any guess, do any guesswork, and build the SQL and then send it to us, because if we are very sure that this is the specific SQL we want to run, then we can hard code it, and then we can, in the tools listing section, we can say that, like, you don't need to supply the SQL. right? The parameter section will be blank, saying nothing. Unlike query here, we have that thing that arguments is SQL. We are saying that you need to SQL, supply the SQL, which will be taken here, and then we'll execute it. See like statements. So yeah, this is the basically how we can build the code. And right now it's running, so we can, the way it runs is right. We have the when I start the cloudy executes the code because it's already defined here in config file. So I'm not running it from VS Code here or anything. It just, everything is cloudy takes care of it. So for example, here we have this. So if I say another query, let's say uh, list top spenders. See that, let's say we make a mistake here. Let's see what happens. So see that this spelling mistake is also taken care of. This is what is good about this kind of search. Uh, so yeah, now we can now we know how to build these things. We can go and do some in-depth technology architecture of this kind of applications, and we can do some interview practice. So we know how to answer the questions in the interview, like what all things are, technology components are involved in this one, and how to talk and answer about this thing. So we can find a job on this kind of work. Ultimately, it will be one thing, but once we have a job, then it's more fun doing this kind of stuff. Bye.
The question that kills 80% of candidates. Our search takes 30 seconds using SQL-like. How would you fix it? The correct answer is Elasticsearch. Here's why.
Yeah, that exact question is a total trap, honestly.
It really is. And if you're listening right now, you are probably a fresh data science graduate gearing up for a really high-stakes, hour-long technical interview.
Right, with a panel of enterprise solution architects, those interviews are intense.
Super intense. Like, you already know SQL inside and out. You can write complex joins, predictive models. But today, our mission is bridging that massive gap from traditional relational databases into the absolute cutting edge of search engine infrastructure and, generative AI.
Because that gap is precisely where most junior candidates just stumble. I mean, the architects interviewing you, they aren't looking for someone who can just query a clean, structured table.
Right.
They want to see if you understand the architectural leap required to search like millions of unstructured documents in milliseconds, and this is the hard part, successfully orchestrate an AI to reason over those documents.
Which requires a completely different mindset. And getting you into that architectural mindset is exactly our mission for this deep dive. But really quickly, before we jump into the deep end, I have to give a huge thanks to Rajan for providing the demo on using Elasticsearch.
Oh yeah, that demo was incredible.
It really was. Seeing that system in action really inspired the technical foundation of the material we're unpacking today.
It was a fantastic demonstration of scale, honestly, and it perfectly complements the stack of sources we've synthesized for you today.
Yeah, let's talk about those sources. What do we have?
Well, we're drawing from actual architectural blueprints for large-scale search. Specifically, we're looking at a really fascinating real-world case study on nannyservices.ca.
Oh, that one is so good.
Yeah, it's super detailed. Plus, we're pulling from cutting-edge academic papers on lexical search optimization, like the recent work on BM25S.
Which we'll get into because the math there is wild.
Oh, absolutely. And then on the AI front, we've integrated comprehensive generative AI interview cheat sheets and technical guides from platforms like Analytics on building enterprise-ready RG systems.
RG being retrieval augmented generation, right. So by the end of this deep dive, you are going to sound like a seasoned architect. So let's just jump straight into the underlying mechanics.
Let's do it.
When that interviewer asks why that SQL query takes 30 seconds, what they're really testing is your understanding of data structures, right?
Exactly. They want to see if you know what happens under the hood. When you execute a SQL-like query with those wildcard percentages, the database is forced to perform a forward index scan.
And we need to visualize what a forward index scan actually physically requires the computer to do. Like, picture a database with 10 million rows.
Right, so the database engine has to pull row number 1 from the disk into memory, scan every single character in the text field looking for your keyword, and then throw it away.
Just discard it.
Yeah, then it pulls row 2, then row 3. It literally does this 10 million times.
Which is insane. I mean, in computer science, we say the time complexity grows linearly with the amount of data. That's O(n).
Right, which is completely fine if you are building, a tiny internal tool with 10,000 records. The CPU can chew through that in a fraction of a second.
But when you hit 100 million rows,
the CPU is just maxed out. Disk I/O bottlenecks, and the whole system just grinds to a halt.
And that's where Elasticsearch comes in, right? The fundamental architecture completely sidesteps this problem by using a totally different data structure, the inverted index.
Yes. And the analogy I always use for the inverted index is a massive textbook.
Okay, lay it out for us.
If you want to find the chapter on thermodynamics, you wouldn't start on page 1 and read every single word in the book until you stumble across the word thermodynamics.
Right. Obviously not. That would take weeks.
Right. But that is exactly what SQL is doing with a wildcard search.
So instead, you'd flip to the index at the back of the book, look up the letter T, find the word thermodynamics, and look at the exact page numbers listed next to it.
Exactly. An inverted index works on that precise logic. Words point to documents, not documents to words.
Okay, so how does that work when data is actually ingested? Let's say document 1 contains the phrase, the sky is blue, and document 2 contains the ocean is blue.
So when Elasticsearch ingests that, it runs an analysis phase. It tokenizes the text, which basically means it chops the sentences up into individual words.
Right.
Then it strips out punctuation, lowercases everything, and builds a centralized dictionary.
So in this dictionary, the word blue becomes a key. Yeah. And mapped to that key is an array of document IDs, right? So document 1 and document 2.
Yep. And the word sky points only to document 1.
And this is the paradigm shift you absolutely must articulate in the interview. When a user searches for the word blue, the engine performs 0 scanning.
0. It executes a direct mathematical lookup for the key blue in its dictionary and instantly retrieves the list of document IDs.
Which changes the time complexity from O(n) to O(1), constant time.
Exactly. The time it takes to find the documents is completely decoupled from how many millions of documents exist in the database.
It's basically magic. I mean, this is the exact mechanism that allowed the team in that nannyservices.ca case study to index 300,000 highly detailed user profiles in just 240 seconds.
And more importantly, it's what allows a search query across all those 300,000 profiles to return in 10 milliseconds.
10 milliseconds. You have to make the architect realize that you don't just know the tool, you know the underlying computer science.
Right. You mentioned that the inverted index is the beating heart of Lucene, which is the underlying library Elasticsearch is actually built on.
But the inverted index only solves the speed problem for exact matches, right? Like if the user types blue, we look up blue.
Yeah, and that's a huge problem because we are dealing with human beings. And human beings type on tiny mobile keyboards.
Oh, the typos.
The typos are endless. If a customer is looking for headphones and they accidentally type HEDPHONES, a rigid dictionary lookup fails completely.
Because there is no key for headphones without the A in our inverted index, SQL would just return a big, empty 0 results page.
And in the enterprise world, especially in e-commerce, a 0 results page is a catastrophic failure. It directly translates to lost revenue.
Right, so a modern search system must gracefully handle human error, which brings us to the concept of fuzzy matching.
Yes, and specifically, The Levenstein distance.
I find Levenstein distance so fascinating because it basically turns spelling into geometry.
It really does. It's a metric that calculates the minimum number of single-character edits required to transform one string of text into another string.
And the allowable edits are insertions, deletions, and substitutions. Right. Let's trace my example. The user types the typo, headphones, without the A. The actual product is headphones.
So the algorithm looks at the two strings and calculates what it takes to bridge that gap. To get from headphones to headphones, we just need to insert the letter A after the E.
That's exactly one edit, so the Levenstein distance is 1.
Exactly. But if they really botched it and typed HETPONES, forgetting the H in phones as well.
And the algorithm recognizes we need to insert an A and insert an H. That's a distance of 2.
Right. But computing this on the fly for millions of potential words is computationally super expensive, because you aren't just looking up one word anymore.
You're mathematically expanding the user's search query to include every possible word in your dictionary that sits within a distance of 2 from their typo.
Which could be hundreds of variations.
So how does Elasticsearch not just crash under that weight?
This is why Elasticsearch provides a highly optimized auto setting for fuzziness. Because as an engineer, you don't want to hard-code a distance of 2 for every single query.
Why not?
Because if a user searches for a short 3-letter word like cat, and you allow 2 typos, it would return words like bat, cut, car, caught.
It would completely dilute the search. You'd get nonsense.
Exactly. The auto setting dynamically adjusts. Words under 3 characters get 0 typos allowed. 3 to 5 characters get 1 typo. Anything longer gets 2.
Oh, that's brilliant. It handles all that complexity behind the scenes so the user gets a seamless experience without crippling the CPU.
Yep. But okay, so we've established how to find the documents incredibly fast, even with typos. Find the documents is only half the battle, though.
Right. If a user searches for running shoes, and your index contains 400,000 pairs of running shoes, how does the engine decide which 10 pairs to show on page 1?
Now you're touching on relevance scoring. We need an algorithm to rank the results. And the undisputed king of lexical relevance scoring is BM25.
Best matching 25. It sounds like a stealth bomber, but it's actually the descendant of the algorithms Google originally used to rank the entire internet.
Exactly. And you need to be able to break down the mechanics of BM25 in an interview. It's built on 3 distinct mathematical pillars.
Term frequency, inverse document frequency, and field length normalization.
Let's isolate term frequency first, or TF. The premise is super intuitive. If you search for the word shoes, a document that mentions the word shoes 20 times is probably more relevant than a document that mentions it only once.
Makes sense. But wait, there is a massive trap there, right? If ranking was purely based on term frequency, it would be so easy to game the system.
Oh, incredibly easy. A merchant could just copy and paste the word shoes 5,000 times at the bottom of their product description and instantly rank number 1.
Right, keyword stuffing. So how does BM25 prevent that?
BM25 introduces a brilliant mathematical concept called term frequency saturation. Unlike older algorithms that scaled linearly where 100 mentions scored 10 times higher than 10 mentions, BM25 uses a curve.
Okay, picture a curve.
The first few mentions of a word drastically increase the score. But as the word appears more and more, the value of each additional mention diminishes and just flattens out.
Ah, so adding shoes for the 1,000th time does basically nothing to your score.
Exactly. It prevents keyword stuffing from destroying your search quality.
Okay, so that handles the frequency of the word within a single document. What about the frequency of the word across the entire database? Like, what if a user searches for the running shoes?
Right. The word "the" is going to have a massive term frequency in almost every document.
This is solved by the second pillar, right? Inverse document frequency, or IDF.
Yes. IDF measures the mathematical rarity of a term across your entire index. Because the word "the" appears in 99% of your documents, its IDF score approaches 0.
So the algorithm effectively penalizes common words. But a term like Nike or Flyknit might only appear in a fraction of a percent of your documents.
And those rare terms carry immensely heavy mathematical weight.
So a document gets a high score if it contains a dense concentration of words that are globally rare. That leaves the third pillar, field length normalization.
Think about where the word is actually found. Imagine 2 documents. Document A is a product title containing just 4 words, vintage leather running shoes. Document B is a massive 5,000-word blog post about the history of cobblers. And buried way down in paragraph 12, it mentions running shoes once.
So even if the term frequency is the same, just one mention in both BM25 inherently understands that a hit in a very short field is vastly more significant than a hit diluted inside a massive wall of text.
Exactly. It normalizes the score based on the length of the field. Shorter fields yield higher scores for matches. This combination TF, IDF, and field length is incredibly powerful.
And it's not a static legacy technology either. One of our sources highlights a recent breakthrough called BM25S.
Oh yes, the BM25S paper. That is fascinating.
It's a highly optimized Python implementation that uses something called eager sparse scoring.
Right, so instead of calculating those scoring components on the fly at query time, it pre-computes them during the indexing phase and stores them in specialized sparse matrices.
And by doing that, they're seeing speedups of up to 500x compared to older Python implementations. 500 times faster.
That is a phenomenal leap in performance. And for a data science graduate, it's a really critical point to bring up in an interview.
Because everyone else is just going to talk about AI.
Exactly. While the entire industry is captivated by AI and dense vectors, the reality is that combining those vectors with ultra-fast, optimized lexical algorithms like BM25 is the actual gold standard for enterprise architecture today.
Okay, so let's shift gears from algorithms to bare metal. Because if you're interviewing for a solution architect role, you cannot just talk about software running on your MacBook.
Definitely not. You have to demonstrate that you understand distributed physical infrastructure. Like, how do we actually store 10 terabytes of inverted indices?
Well, you essentially have two choices: scale up or scale out. Scaling up, or vertical scaling, means taking a single server and just continually adding more RAM, more CPU cores, and larger hard drives.
But you hit a ceiling very quickly there. A motherboard can only hold so much RAM.
And even if you could build a supercomputer with 10 terabytes of RAM, it becomes astronomically expensive. And worse, it's a single point of failure. If that machine's power supply blows,
Your company's entire search infrastructure is offline, which is why enterprise systems like Elasticsearch rely on scaling out horizontal scaling.
instead of one massive supercomputer, you use a cluster of smaller, cheaper commodity servers. We call these individual servers nodes.
But how do you spread 10 terabytes of data across multiple nodes? You use a process called sharding.
Okay, so you take that massive 10 terabyte index and you mathematically slice it into smaller, manageable chunks, say 50 distinct pieces of 200 gigabytes each. Each of these pieces is a primary shard.
You then distribute those 50 shards evenly across your cluster of nodes. The brilliance of this architecture is parallel processing.
Right, because when a user executes a search query, that query isn't just processed by one machine anymore.
Exactly. A coordinating node receives the request and broadcasts it simultaneously to every shard in the cluster.
So each node searches its local 200 gigabyte chunk of data at the exact same time, and then they return their individual top results back to the coordinating node.
Which merges them into a single master list. You are literally harnessing the CPU power of the entire cluster for every single query.
It's amazing. But sharding only solves the compute bottleneck. What happens when a physical server inevitably fails? Because hardware fails all the time.
It does. If node 3 catches fire and it holds shards 10 through 15, you just lost a critical portion of your database.
This is where the concept of replication becomes vital. A replica is an exact byte-for-byte copy of a primary shard.
But there is a golden rule here. A replica must never ever reside on the same physical node as its primary shard.
Right, because if the node burns down, you lose the primary and the backup. So if Elasticsearch places primary shard 1 on node A, it will deliberately place replica shard 1 on node B.
Exactly. So if someone accidentally unplugs node A from the server rack, the cluster immediately detects the loss of heartbeat.
And within milliseconds, it promotes the replica on node B to become the new primary shard. It seamlessly reroutes all incoming search traffic.
The system achieves high availability. A user executing a search during that hardware failure wouldn't even notice a blip in performance.
Understanding that physical resilience is what separates a junior developer from a systems architect. Now, up until this point, we've focused on exact words, typos, and keyword relevance.
Right, lexical search.
But what happens when a user doesn't know the exact keyword? What if they search for comfortable chair?
Well, a lexical engine like BM25 is just looking for the letters CHAIR. It might completely fail to retrieve a product titled ergonomic mesh seating, even though it's exactly what the user wants.
And this limitation is the catalyst for the biggest revolution in search history. vector search and semantic embeddings.
We are finally moving away from looking for matching letters and moving toward calculating matching meaning.
But how does a computer compute meaning? It translates language into geometry?
It uses deep learning models, specifically embedding models, to read a document and map its semantic meaning into a list of hundreds or even thousands of floating point numbers.
These numbers represent a coordinate in a massive, high-dimensional mathematical space.
Imagine a massive 3D graph, but instead of just an X, Y, and Z axis, there are 768 different axes.
My brain hurts just trying to picture that.
I know, it's abstract.
Yeah.
But the embedding model is trained on billions of parameters to ensure that concepts with similar meanings are plotted physically close to each other in this space.
So the coordinate for comfortable chair is mathematically positioned right next to the coordinate for ergonomic mesh seating because their semantic intent is nearly identical, regardless of the vocabulary used.
Yes. So when the user types their query, the engine doesn't look at an inverted index. It converts the user's query into a vector, plots it on that massive graph, and runs an algorithm to find the nearest neighboring coordinates.
It's using spatial distance to determine semantic relevance. But implementing this requires specialized index structures, right? You can't just scan a list of millions of vectors to calculate the distance between them.
No, that would be ON all over again. Modern vector search relies on algorithms like HNSW, which stands for Hierarchical Navigable Small World Graphs.
That's a mouthful.
It is. But basically, it creates a multi-layered web of connections between vectors, allowing the search engine to rapidly traverse the graph and approximate the nearest neighbors in milliseconds.
Which brings us to the ultimate architectural question. We've established that Elasticsearch handles lexical matching flawlessly, and it can store and query these massive vector embeddings for semantic search. So why do we need traditional databases at all?
Oh, the classic question.
Why not just build the entire company's backend on Elasticsearch? This introduces a critical enterprise pattern you absolutely must master, the PostgreSQL plus Elasticsearch dual database architecture.
This is a classic system design test. An architect will challenge you. We have PostgreSQL. It's rock solid. Why introduce the massive complexity of a second database technology and duplicate all our data?
On the surface, it sounds incredibly inefficient. You are storing your inventory data in Postgres, and then you are copying that exact same text data into Elasticsearch just to search it. Your storage bill doubles. How does an architect justify that?
By understanding the fundamental limitations of database paradigms. PostgreSQL is a relational database designed around ACID compliance, atomicity, consistency, isolation, durability.
Basically, the rules that keep your data safe.
Right. If a customer purchases the last ergonomic chair in stock, Postgres absolutely guarantees that two concurrent users cannot both buy that same chair. It locks rows, processes transactions, and maintains strict data integrity.
It is the uncompromising source of truth.
But that strict consistency comes at a huge performance cost. Postgres does have full-text search capabilities using GIN indices, but when you throw complex, fuzzy, multi-field aggregations at it across millions of rows, it bottlenecks hard.
Conversely, Elasticsearch is a distributed, NoSQL search engine. It is designed to ingest massive volumes of unstructured data and return highly relevant search results instantly.
But is not strictly ACD compliant by default. You do not want to use Elasticsearch to process financial transactions.
Please don't. So you separate the concerns. Postgres handles the high stakes, transactional writes. Elasticsearch handles the complex, heavy read queries from the search bar.
But the real magic is how you connect them. You don't write custom cron jobs to copy data over every hour. You implement CDC, change data capture.
Using an infrastructure tool like Debezium, right?
Exactly. Debezium sits at the infrastructure layer and silently monitors the Postgres write-ahead log as the deepest, lowest level ledger of every single change made to the database.
So the very millisecond a product price is updated or a new description is saved in Postgres, Debezium captures that discrete event and streams it asynchronously into Elasticsearch.
The search index is updated in near real time, completely independently of the main application code. The web servers don't even know it's happening.
That separation of concerns, the fault tolerance of CDC, and the optimization of distinct database technologies for distinct workloads, that is what true enterprise architecture looks like.
Absolutely. And this transitions us perfectly into the actual interview simulation, because knowing these concepts in isolation is great, but synthesizing them under pressure when a panel of architects is staring at you, that's a different game entirely.
Let's walk through how to deliver the answers they actually want to hear. Let's set the stage. The lead architect leans across the table and throws the first test at you.
We are migrating our legacy backend. Why should we spin up and maintain a whole separate Elasticsearch cluster when PostgreSQL already has a built-in full-text search feature? Convince me it's worth the operational overhead.
This is a total trap. If you just say Elasticsearch is faster, you fail.
Instantly.
You need to provide a structured, multi-pillar defense that proves you understand the physical limits of relational databases. So how do you construct that answer?
You structure it around 5 undeniable architectural advantages. You start by validating their premise, then pivoting. You say, PostgreSQL full-text search using GIN indexing is an excellent lightweight solution for applications with fewer than 100,000 documents. But for a production-scale application, we will rapidly hit a ceiling. I advocate for Elasticsearch for 5 specific reasons.
Okay, hit them with pillar 1.
Scale. Postgres requires complex partitioning to scale horizontally. Elasticsearch uses native sharding and replica allocation out of the box, allowing us to distribute terabytes of index data across commodity hardware effortlessly.
You too.
Fuzzy matching and relevance. Postgres text search is rigid. Elasticsearch handles Levenshtein distance computations efficiently, drastically reducing zero results pages from typos, and uses highly tunable BM25 scoring out of the box to drive better relevance.
Pillar 3.
Real-time capability. With a CDC pipeline, Elasticsearch can ingest changes and make new documents searchable within 1 second without locking up our transactional database tables.
Pillar 4.
Analytics. Elasticsearch uses specialized column-oriented data structures called doc values, allowing us to run complex, multifaceted aggregations like counting inventory by category, size, and color orders of magnitude faster than a traditional SQL Group PY clause.
And finally, pillar 5.
Future-proofing for AI. Elasticsearch natively supports dense vector embeddings and highly optimized HNSW graph retrieval, allowing us to seamlessly integrate semantic search and RAG pipelines without bolting on yet another vector database later.
Boom. When you lay out those 5 pillars calmly, the architect knows immediately that you aren't just reciting a tutorial. You have a deep, holistic grasp of data engineering.
But then they will escalate. They'll move from theory to system design.
Right. Question 2. The architect says, all right, I buy it. We use Elasticsearch. Now, design a search system for our e-commerce catalog of 10 million products. Give me the infrastructure specs.
And our critique of the sources highlighted a crucial error candidates make right here. Do not just memorize a random server configuration you read on a blog like, I would use a 10-node cluster with 20 shards.
Yeah, because if you say that, the architect will instantly ask, why exactly 20 shards? And if you don't know the math, the interview is over. You must explain the variables and the formulas.
Precisely. You approach it mathematically. You say, first, we need to calculate the storage footprint. If we have 10 million products, and each product's JSON document, including text, metadata, and dense vectors, averages 2 kilobytes, our total primary data is roughly 20 gigabytes.
And the golden rule of Elasticsearch sharding is keeping individual shards between 10 to 50 gigabytes for optimal performance and recovery time.
Therefore, for 20 gigabytes of data, we actually only need a single primary shard to start, perhaps scale to 2 or 3 shards if we anticipate heavy write throughput. Oversharding is a massive anti-pattern that creates unnecessary network overhead.
Then you move to memory management, which is a fantastic place to show off deep systems knowledge.
Oh, this is where you talk about the JVM heap. Elasticsearch runs on the Java virtual machine, so you explain. I would provision nodes with 64 gigabytes of RAM, but crucially, I would strictly limit the JVM heap size to exactly 32 gigabytes.
Wait, why limit it to half the RAM?
You explain. Because going above 32 gigabytes forces Java to disable compressed ordinary object pointers. The pointers suddenly take up twice as much space, meaning a 40 gigabyte heap actually holds less usable data than a 30 gigabyte heap.
Wow.
The remaining 32 gigabytes of system RAM is deliberately left free for the operating system's file system cache, which Lucene relies on heavily for fast index reading.
That level of detail understanding the low-level garbage collection mechanics of Java pointers will absolutely drop the jaw of the architect.
It really will. And then you round out the design by discussing lifecycle management. To control cloud costs, I would implement ILM Index Lifecycle Management. Our actively searched in-season products sit on high-performance hot nodes with NVMe SSDs. Older, discontinued products migrate automatically to cheaper warm nodes using standard block storage.
But a great candidate knows that designing the system is only half the job. You have to design the observability of the system. You must mention monitoring.
I would also implement strict telemetry. We need to monitor slow query logs, JVM garbage collection pauses, and crucially, monitor the CDC sync lag from Debezium. If our search index falls 5 minutes behind our source of truth, we have a massive data integrity issue.
Which perfectly tees up the third and most difficult question, the disaster scenario.
Oh, they love this one. The architect asks, okay, you've built this CDC pipeline. What happens when the network fails? PostgreSQL updates a product price from $100 to $50. Debezium attempts to send that update, but the Elasticsearch cluster experiences a temporary network partition. The message is dropped. Your search index still shows $100. How does your architecture handle this inconsistency?
This is the nightmare of distributed systems. Eventual consistency failing to eventually be consistent. How do you architect a bulletproof recovery?
You calmly outlined a multi-layered fault tolerance strategy. First, at the messaging layer, we use a robust broker like Apache Kafka. We configure a dead letter queue.
A DLQ.
Exactly. If Elasticsearch fails to acknowledge the write, Kafka catches the message, drops it into the dead letter queue, and triggers an automated retry mechanism utilizing exponential backoff waiting 1 second, then 2, then 4, so we don't overwhelm a recovering cluster.
But what if the messages arrive out of order? The network recovers, and suddenly the $100 price update arrives after the $50 update.
That is solved by our second layer, idempotent writes using external versioning. Every single update from Postgres includes a precise timestamp or transaction ID. We configure Elasticsearch to only accept writes if the incoming version number is strictly greater than the currently stored version. If an older message arrives late, it is safely ignored.
Brilliant. And for ultimate peace of mind, Layer 3, the reconciliation job. Every Sunday at 2 a.m. during our lowest traffic window, a background script performs a cryptographic checksum comparing the Postgres inventory table against the Elasticsearch index, automatically detecting and healing any silent discrepancies.
If you deliver those answers, calculating shard size dynamically, explaining JVM pointer compression, and architecting fault-tolerant dead letter queues, you haven't just passed the system design interview. You've proven you can build enterprise-grade infrastructure.
But here is the reality of the modern tech landscape. Being a master of search infrastructure is now just the baseline requirement.
Yeah, unfortunately for candidates, the bar just keeps moving up.
Today's enterprise architects demand deep, practical knowledge of the AI layer that sits directly on top of that search infrastructure. The industry is rapidly transitioning from traditional search architects to AI architects.
It is no longer sufficient to simply retrieve a relevant document and hand it to the user. You have to understand exactly how a large language model ingests that document, reasons over it, and generates a coherent, hallucination-free answer.
This takes us into part 3, generative AI job skills readiness. Let's start by demystifying the fundamental engine of Gen AI. When we say an LLM like GPT-4 or Claude understands text, what is actually happening physically inside the processor?
We need to unpack the transformer architecture and the mathematical elegance of self-attention.
Self-attention is the mechanism that allows a model to understand context and relationships between words, regardless of how far apart they are in a sentence. Let's use a classic linguistic example. The cat sat on the mat because it was tired.
When a human reads that sentence, our brain intuitively resolves the pronoun. We know the word it refers to the cat, not the mat. Mats are inanimate objects. They don't experience fatigue.
But how does a cluster of GPUs calculate that understanding?
Through the mathematical calculation of attention scores. During processing, the model generates 3 distinct vectors for every single word in that sentence: a query vector, a key vector, and a value vector.
Think of it like a database operation happening inside the neural network. The query vector for the word it is essentially broadcasting a mathematical signal. I am a pronoun, and I am looking for a noun that is capable of being tired.
Simultaneously, the key vector for the word cat is broadcasting its semantic properties. I am an animate noun capable of exertion. And the key vector for mat broadcasts. I am an inanimate object.
The model then calculates the dot product, a mathematical multiplication between the query vector of it and the key vectors of every other word.
Because the model has been trained on terabytes of human language, the mathematical alignment between a pronoun looking for exhaustion and an animate noun creates a massive numerical spike. The attention score between it and cat surges to 0.9, while the score for mat drops to 0.01.
The model mathematically bonds the two words together. It passes that weighted context forward using the value vectors.
This dot product calculation happens millions of times per second across multiple attention heads. But there is a severe mathematical catch that every architect must understand.
What's the catch?
The computational cost of self-attention scales quadratically.
Let's explain what quadratic scaling means in practice, because it sounds scary.
It is scary for your cloud bill. If you double the length of the text you feed into the model, the amount of computational work doesn't double, it quadruples. If you increase the text by 10x, the computation increases by 100x. The matrix multiplications just explode in size.
This geometric explosion of compute is the precise architectural reason why large language models have strict context limits. You physically cannot feed an entire gigabyte-sized database into the model's prompt.
Right. And even if you have a massive 128,000 token context window, relying on it creates a massive vulnerability known as the lost in the middle problem.
Yeah, I've seen this happen.
Research has proven that when you dump a massive 100-page PDF into an LM's context window, the attention mechanism becomes saturated. The math is stretched too thin across millions of cross-calculations.
The model pays strong attention to the very beginning of the document and the very end, but it drastically loses focus on the information buried in the middle. It will confidently fail to retrieve facts located on page 50.
Which means the entire paradigm of just upload the whole document to the AI is fundamentally flawed for enterprise reliability.
We need a system that acts as a highly precise filter, a system that searches our massive database, finds only the 2 or 3 most perfectly relevant paragraphs, and feeds just those paragraphs to the model. We need R, Retrieval Augmented Generation.
If an architect asks you to design a RAG pipeline on a whiteboard, clarity is everything. You must divide the architecture cleanly into 2 distinct, decoupled phases: the offline ingestion phase and the online generation phase.
Let's walk through the offline phase first. This is the infrastructure you build before a user ever types a question. You have a massive repository of company data, employee handbooks, technical runbooks, financial reports.
Step 1, data parsing and cleaning. You strip out the HTML, the complex table structures, the weird PDF formatting.
Step 2, chunking. This is arguably the most critical and overlooked step. You cannot embed a 50-page document as a single vector. You must slice the document into smaller, semantically meaningful paragraphs or chunks.
And this requires real engineering judgment. If your chunks are too large, say an entire chapter, you waste the LLM's context window and risk the lost in the middle problem during retrieval.
But if your chunks are too small, like a single sentence, you destroy the semantic context. Like a chunk that just says coverage begins on the 1st of the month is completely useless if the retriever didn't also grab the preceding sentence that specified whether it was talking about dental insurance or server warranties.
Exactly. Finding the optimal chunk size, usually a few hundred tokens with a configured sliding window of overlap to preserve context boundaries, is an iterative process.
Okay, so once chunked, step 3.
Yeah.
You pass every chunk through an embedding model to generate its dense vector representation. Step 4. You store the text chunk and its corresponding vector in a vector database.
That's the offline pipeline. The database is prepped. Now, the online phase. It's Tuesday morning. A junior developer logs into the internal portal and types, "How do I reset the staging database?"
The pipeline kicks into gear. First, we take the user's raw question and pass it through the exact same embedding model used in the offline phase, generating a query vector.
Second, we execute a nearest neighbor vector search against our vector database, calculating the mathematical distance to find the top K chunks, the 5 paragraphs that most closely align with the user's intent.
Third, the orchestration layer grabs those 5 paragraphs of text and injects them into a highly structured prompt template alongside the user's original question.
The system prompt essentially instructs the LLM. You are an expert engineering assistant. Answer the user's question using only the factual context provided below. If the answer is not contained in the context, say, "I do not know." Do not invent information.
Finally, the LLM reads that tightly constrained prompt, synthesizes the injected paragraphs, and streams back a highly accurate, context-aware answer.
Why is this architecture dominating the enterprise? Why do CTOs heavily prefer building complex RAG pipelines over just fine-tuning their own proprietary models?
3 massive advantages. Number 1, cost and velocity. Updating a database is virtually free. If the company changes its vacation policy on Friday, with R, you just delete the old document vector and ingest the new one. The AI is instantly updated.
With fine-tuning, you would have to spend tens of thousands of dollars on GPU compute and days of training time trying to force the model's neural weights to forget the old policy and learn the new one.
Number 2, auditability. RAG shifts the fundamental psychological behavior of the LLM. It stops acting like a student guessing answers on a closed-book test based on faint memories of its training data.
It becomes an open-book test. It acts as a synthesizer of provided evidence.
Which leads to number 3, mitigating hallucinations. Because the RAG pipeline provides the exact source paragraphs, the LLM can explicitly cite its sources in the UI. If the AI gives an answer, the user can click a footnote and read the exact paragraph from the employee handbook.
It builds trust, which is the currency of enterprise software. But the success of this entire pipeline hinges on the retrieval component. If your database retrieves the wrong 5 paragraphs, the LLM will confidently give the wrong answer.
You need to understand the vector database landscape. It is exploding right now, and an architect will expect you to have strong opinions on the tools. Let's contrast the major players.
If you want zero operational overhead and your company is fully cloud native, you look at Pinecone. It's a fully managed proprietary service. You just send it vectors via an API, and it handles the complex HNSW graph building behind the scenes. The trade-off is vendor lock-in and potentially steep costs at massive scale.
What if the company has strict data privacy compliance and needs to run everything on their own private servers?
Then you look at open source heavyweights like Weaviate or Milvus. Weaviate is exceptional because it has native built-in support for hybrid search pipelines, managing both lexical and vector indices simultaneously. But self-hosting requires serious DevOps expertise to manage cluster stability.
What if I'm just building a lightweight local prototype?
You reach for Chroma. It's incredibly lightweight, running entirely within your Python process, acting much like Squeal does for relational data. It is fantastic for rapid iteration, though you wouldn't deploy it as a standalone server for billions of vectors.
And what if the chief technical officer absolutely refuses to add yet another database technology to your already complex tech stack?
You leverage PG Vector. It is a powerful extension for PostgreSQL that adds native vector storage and indexing right alongside your relational tables. It allows you to run a SQL query that filters on strict business logic like only search products in stock and immediately calculates the nearest neighbor vector distance in the same query.
It's an incredibly elegant, unified solution, though it requires careful tuning to match the extreme millisecond latency of purpose-built vector databases.
Now, you mentioned Weaviate's strength in hybrid search. I want to drill deeply into this because our sources are very explicit. Deploying a purely semantic vector search in an enterprise environment is actually a massive risk.
Why is pure semantic search sometimes completely inadequate?
Because semantic search is optimized to understand broad intent, but it mathematically blurs hyper-specific details. Vector models are terrible at handling exact technical tokens.
Let's play out a scenario. A site reliability engineer is diagnosing a critical outage. They search the internal knowledge base for a highly specific alphanumeric string. Error 403 quota exceeded.
If you pass that exact string into a pure dense vector model, the model analyzes the semantic intent. It thinks, oh, quota exceeded, this user is asking about general API rate-limiting concepts.
It plots the vector in the rate-limiting neighborhood.
Exactly. The database retrieves 5 highly generic architectural documents explaining how rate limiters work in theory, but it completely fails to retrieve the exact specific runbook for that error code because the exact letters were smoothed over by the semantic math.
This is exactly why we spent the first 20 minutes of this deep dive obsessing over BM25 and traditional lexical search. BM25 is literal. It doesn't care about the philosophy of your intent. It looks for the exact occurrence of the letters ERR403.
If that string exists in a document, BM25 will find it instantly.
The modern enterprise architecture mandates hybrid search. You execute both queries simultaneously. You run the user's input through the dense vector index to capture semantic meaning, and you run it through the BM25 inverted index to capture exact keyword matches.
But then you have 2 completely different lists of results scored on completely different mathematical scales. BM25 scores might range from 10 to 50, while vector cosine similarity scores range from 0 to 1. How do you merge them into a single, ranked topcock to feed to the LLM?
You implement a mathematical fusion algorithm, the most common being RRF, reciprocal rank fusion. RRF ignores the raw scores completely. It only looks at the absolute rank position of a document in both lists.
If a document ranks number 2 in the vector search and number 4 in the keyword search, RRF calculates a combined score based on those positions. Documents that appear near the top of both lists are heavily boosted to the absolute top of the final results.
It's the best of both worlds. And in practice, architects usually expose weighting parameters, starting with a baseline split, perhaps applying 70% weight to the semantic results and 30% to the lexical results, and tuning it based on analyzing real user query logs.
This deep understanding of retrieval failure modes leads us to one of the most fascinating insights from our stack of sources today. It comes from a paper analyzing a system called Kara1, and it details what they define as the scaling disaster of semantic search.
This is critical for an architect interview. You have to demonstrate that you understand how systems degrade as they grow. Semantic search feels like absolute magic when you were building a small proof of concept demo with 5,000 documents on your laptop. Every query returns the perfect document.
But when you deploy to production and index 50 million enterprise assets, the retrieval quality mysteriously collapses.
The accuracy plummets, and the LLM starts hallucinating because it's being fed garbage context. Why does the math break at scale?
Our sources use a brilliant visualization, the dartboard versus the chessboard.
Let's unpack this analogy. In an ideal, mathematically perfect retrieval system, a chessboard, every single document has its own distinct, equally sized square. Every asset is equally reachable. If you aim your query vector at square D7, you retrieve the document at D7.
But high-dimensional vector space, created by complex human language, does not map neatly to a chessboard. It warps into something resembling a distorted dartboard.
What causes the physical distortion of the space?
The phenomenon is driven by the density of generic language. In any massive corporate dataset, some concepts are incredibly dense, broad, and somewhat related to everything. Think of words like synergy, user experience, or platform integration.
The vector embeddings for documents heavily featuring these concepts become massive gravitational anomalies. They act like giant, disproportionate wedges on the outer rim of our conceptual dartboard.
Because they share a slight semantic overlap with almost any query, they cast a massive gravitational pull in the vector space. We call this the hubness problem.
Exactly. So when a user throws a highly specific query dart, aiming for a tiny, rare, hyper-specific document, the tiny bullseye, the geometry of the space, fails them. The massive gravitational pull of the generic hub documents alters the trajectory of the nearest neighbor calculation.
The query gets sucked into the massive wedge. The retrieval system spams the user and the LLM with the same 5 mediocre high-level overview documents over and over again, while the precise, obscure runbook you actually need becomes mathematically unreachable at scale.
The Kara 1 paper outlines that to solve this at enterprise scale, you cannot just rely on basic embeddings. You have to apply custom post-processing mathematical models, essentially creating a specialized transformation matrix that acts as a pair of corrective glasses for the vector database.
You mathematically stretch and remap the warped dartboard back into a clean, uniform chessboard, suppressing the gravitational pull of generic HUD documents and ensuring that highly specific, rare assets have an equal mathematical chance of being surfaced.
If you can sit across from an enterprise architect and clearly articulate the hubness problem, vector space distortion, and how to correct it at scale, you aren't just passing the interview, you are establishing yourself as a peer.
But we cannot stop at retrieval. The final piece of the GenAI puzzle requires moving beyond just answering questions. We have to talk about agentic AI and the model context protocol.
Everything we have discussed so far regarding the AG is fundamentally a single-pass, read-only system. The user asks a question, the system retrieves context, the LLM reads it, and generates an answer. It's a straight line.
But the bleeding edge of the industry is transitioning to agentic systems, systems that execute iterative, multi-step reasoning loops and take actions.
You aren't just giving the LLM a prompt, you are giving it autonomy, a suite of tools, and a framework to solve complex, multi-stage problems. Let's break down the architecture of an agentic system. It typically requires introducing specialized roles like the planner and the executor.
Imagine a business user asks a complex query. Compare our Q3 server infrastructure costs stored in our AWS billing database against the Q3 revenue growth projected in the PDF marketing strategy deck, and draft a summary.
A traditional single-pass RJOG system completely fails here. It cannot query a SQL database and read a PDF in the same motion.
This is where the planner agent steps in. It receives the complex query and uses its reasoning capabilities to break it down into a multi-step execution graph. Step 1, query the SQL database for the AWS billing data. Step 2, query the vector database for the marketing PDF chunks. Step 3, wait for both results. Step 4, synthesize the data into a summary.
The planner then delegates these specific tasks to specialized executor agents. Orchestrating this complex, asynchronous back and forth requires robust infrastructure. You cannot manage this with fragile Python-wall loops.
You use advanced orchestration frameworks like LangGraph. LangGraph introduces the concept of state management to LLM interactions. It handles the routing, ensuring the JSON output of the SQL query agent is correctly formatted and passed as the input to the synthesis agent. More importantly, it handles state persistence and automatic retries.
If the agent executing the SQL query encounters a syntax error, LangGraph catches the failure. It persists the memory of the error, feeds the error message back to the agent, and essentially says, your SQL query failed with this error, fix the syntax, and try again. The agent iteratively corrects its own mistakes without human intervention.
But how do these intelligent agents physically interface with the outside world? How does an LLM securely connect to an Elasticsearch cluster or a Postgres database? This brings in the most critical new development from our sources, MCP, the Model Context Protocol.
Let's explain why MCP is so revolutionary. Historically, if you wanted your LLM to execute a search query against your Elasticsearch database, a backend engineer had to write custom, brittle, hard-coded integration scripts. If you later wanted the LLM to read files from a local directory, you had to write another set of custom scripts. It was a maintenance nightmare.
MCP eliminates this friction completely. It is best understood as the USB-C standard for AI. It is an open-source protocol that standardizes exactly how AI models discover and connect to external data sources and tools. It operates over a standardized JSON RPC interface.
How does it work in practice? You spin up an independent MCP server that sits in front of your Elasticsearch cluster. That MCP server securely exposes a standardized tool definition, essentially broadcasting to the network. I have a tool called Search Enterprise Documents. It requires 2 parameters, a QWERTY string and a date range.
When the LM agent is spun up, it dynamically connects to the MCP server. It reads the JSON schema of available tools. It actually learns what tools it has at its disposal in real time. When the planner agent decides it needs to search for documents, it doesn't need custom Python code. It simply formats a standardized JSON response calling the Search Enterprise Documents tool. The MCP server validates the request, executes the actual Elasticsearch query securely, and passes the results back to the agent.
It completely decouples the cognitive reasoning of the AI from the physical infrastructure of the tools. You can swap out the backend database entirely. And as long as the new database has an MCP server, the AI agent doesn't need to change a single line of its prompt logic. It is the architectural foundation that will allow AI agents to scale reliably in the enterprise.
We've just sprinted through an incredibly deep, exhausting technical gauntlet, from the low-level memory allocation of Lucene inverted indexes to the mathematics of vector space distortion to the orchestration of autonomous LangGraph agents via MCP.
But here's the harsh, unavoidable truth of the tech industry. You can be the greatest technical architect in the world, you can understand the math perfectly, but if you cannot communicate effectively in a room full of stakeholders, you will not get the job offer. An interview is not just a test of knowledge, it is a test of collaboration. So, we must pivot to part 4, dominating the HR and behavioral interview.
Enterprise architects are not just evaluating whether your code compiles, they are evaluating how you think through ambiguity, how you justify your architectural trade-offs, and crucially, how you react when you don't know the answer. The evaluation begins the exact second they ask the standard opener. Tell me about yourself.
Most candidates fundamentally misunderstand this prompt. They treat it as an invitation to recite their resume chronologically. I grew up here, then I went to this university, then I took a course on Python, then I learned SQL. It is rambling, it lacks focus, and it instantly bored the panel. How should a solution architect structure their introduction?
You must use a precise, tight narrative flow. Current role, relevant experience, major impact, and strategic alignment. Keep it under 90 seconds. You say, I'm a recent data science graduate with a deep focus on NLP and distributed systems. Over the past year, my relevant experience centered on optimizing search infrastructure, specifically architecting a hybrid RAG pipeline that merged BM25 lexical scoring with dense vector retrieval. That project successfully reduced query latency by 20% while eliminating search hallucinations. I am incredibly excited about this role because I see your company transitioning toward agentic AI workflows, and that is exactly where I want to apply my system design skills.
Notice the deliberate framing. You didn't just list technologies, you listed the impact of those technologies. Reduced query latency by 20%. Which brings us to the absolute gold standard for answering behavioral questions, the STAR method.
Situation, task, action, result. When a panelist asks, tell me about a time you faced a complex technical challenge, do not launch into an unstructured ramble about how hard a bug was to fix. You must structure the narrative.
Situation. Provide the absolute minimum context required. Our legacy SQL database queries for the product catalog were timing out under heavy load.
Task. Define your specific responsibility. I was tasked with redesigning the retrieval architecture to bring P99 latency under 100 milliseconds.
Action. Explain exactly what you did, focusing on the architectural decisions. I designed a migration path to move the unstructured text fields into an Elasticsearch cluster. I implemented a Debezium CDC pipeline to stream updates from Postgres and configured a custom BM25 analyzer to handle our specific industry jargon.
Result, close with measurable business-level impact. Search latency dropped from 30 seconds to 50 milliseconds, and the reduction in zero results pages correlated with a 5% increase in weekly conversion rates.
It is a framework that forces you to be concise, logical, and impactful. But let's push back on the reality of technical interviews. They aren't going to just let you recite practiced stories. They will try to break you. What happens when they throw a massive curveball? What if the lead architect asks you to whiteboard a high-throughput streaming architecture using Apache Kafka, and you have literally never touched Kafka in your life? You've only used RabbitMQ for simple messaging.
This is the ultimate stress test. They often ask questions they suspect you don't know, specifically to see how you handle the unknown. The absolute worst thing you can do is freeze. The second worst thing you could do is try to fake it. They have spent a decade working with Kafka. They will see through your bluff in 10 seconds, and your credibility will be permanently destroyed.
So what is the tactical play? How do you survive the curveball?
You acknowledge the gap with absolute calm, and then immediately demonstrate your ability to bridge concepts using structured reasoning. You say, to be completely transparent, I have not deployed Kafka in a production environment. However, I am deeply familiar with the core principles of message brokers through my extensive work with RabbitMQ. Assuming Kafka operates on a similar foundational paradigm of producers, persistent topics, and consumer groups, here is how I would logically approach architecting this data pipeline.
You admit the gap, you pivot to a related technology you do understand, and you proceed to attempt the problem conceptually. It shows immense confidence. It shows that you view technologies merely as tools that share underlying computer science principles, which is the exact mindset of a senior architect.
And this brings us to the final moments of the interview. The panel closes their laptops, looks at you, and asks the obligatory closing question. Do you have any questions for us?
Junior candidates ask about vacation policies or what a typical day looks like or what the lunch menu is. Great candidates realize this is their final opportunity to prove they belong in the room. You must ask incisive questions back. You must interview them.
Ask questions that prove you understand the friction of enterprise engineering. Ask about operational culture. We talked a lot today about deploying advanced ORAG pipelines. In your current engineering culture, how do you manage the natural friction between shipping experimental AI features quickly and ensuring strict data governance and compliance?
Ask about business alignment. How do the specific search and AI infrastructure initiatives we discussed today tie into the broader company revenue strategy for the next fiscal year?
When you ask questions that elevate the conversation from lines of code to business strategy and organizational dynamics, you completely reframe their perception of you. You elevate yourself from a junior coder who just takes Jira tickets to a strategic partner they want in the room when hard decisions are made.
All right, let's take a breath and recap the incredible depth of this journey. We started by mastering the bare metal mechanics of Elasticsearch, understanding exactly how the inverted index circumvents O-lens scanning, how Levenstein distance elegantly maps human typos, and how BM25 math mathematically prevents keyword stuffing while surfacing true relevance.
We tackled a system design interview, proving we know how to calculate shard sizes, manage JVM heap constraints, and defend the robust PostgreSQL to Elasticsearch CDC pipeline using dead letter queues for fault tolerance.
We navigated the sheer complexity of the generative AI layer, unpacking the quadratic scaling limits of self-attention transformers, the critical importance of semantic chunking in the RAG pipeline, and the mathematical necessity of hybrid search to overcome vector space distortion. We looked at the frontier of agentic AI, where planner and executor agents use LangGraph and the Model Context Protocol to autonomously interact with enterprise tools.
And finally, we locked down the behavioral interview, ensuring you can articulate your impact using the STAR method and confidently handle knowledge gaps under pressure. You are walking into that interview room armed with a holistic architectural understanding of the entire modern data stack.
But before we sign off, we want to leave you with a final puzzle, something deeply complex to mull over as you prepare for the future of this industry.
We've talked extensively today about ensuring our AI accurately retrieves the most perfectly updated information from our databases. We have optimized the read paths. But as we move fully into the era of agentic AI systems that use tools like MZP not just to read data, but to autonomously write, update, and execute transactions across our databases, a profound new architectural challenge emerges.
How do we evaluate hallucinations when the AI is no longer just answering questions, but autonomously altering the very source of truth it relies on? If an autonomous agent hallucinates a database update, say, incorrectly changing a product's price based on a misunderstood PDF, that corrupted data becomes the new factual reality for the next agent that queries the database.
The feedback loop of error becomes institutionalized. How do we build deterministic guardrails for a non-deterministic machine that possesses the ability to rewrite its own history?
That is the architectural problem that will define the next decade of data science. Thank you for joining us on this deep dive. Take these concepts, practice your delivery, understand the why behind the architecture, and go crush that interview. And remember, when they ask why that SQL IRQ query is killing their servers, you know exactly what to tell them.